This deck introduces normalization and explains database anomalies. Of course, to master these concepts, you will have to apply them. Experts have spent years figuring out how to organize data to help computers more effectively process data. Good data design organizes data into useful data structures that facilitate either operations or analysis, and we call this kind of process, this breaking up of data into useful lists, normalization. By definition, normalization is a process for evaluating and correcting table structures to minimize data redundancies, thereby reducing the likelihood of data anomalies. If we take that definition and break it down, we can see four important points. When organizers normalize their data, they're applying structure to the data. Those structures consist of a set of lists, which are called tables. Each table in a design is a list of a certain kind of thing. It's important to pay close attention to redundancy. That is, we should avoid storing the same data twice in our design. And finally, normalization concepts allow us to systematically compare alternative data structures to see which is better at avoiding commonly understood problems called anomalies. Did you catch that definition? Normalization applies structure to data. We normalize by breaking up our data into multiple lists. Normalization rules allow us to compare different possible structures to see which is better and worse. Normalized lists avoid storing the same data points twice. Some common things happen when you have a bad data design. We call these things database anomalies. Update anomalies occur when the same data is stored in multiple places. This storing in multiple places makes it hard for the system to keep things straight. If, for example, you store a customer's email address in several lists, it's harder to update it when it changes. You have to find that bit of data in all the places it is stored if you're going to make the change. Insert anomalies arise when there is no place to properly store needed data. For example, if you only keep a list of sales, where would you store a record for a new customer who has not yet bought anything? Delete anomalies, the third type, come up when deleting something from one list results in the loss of some related data. For example, if you kept only a list of cars associated with parking permits, and someone sells one car but hasn't registered a new one yet, deleting that car might result in completely losing track of the permit. Database experts have analyzed how these anomalies can be avoided by ensuring data models comply with a series of normal forms. These forms are carefully described in many widely available resources, and they are a systematic and precise way of identifying potential database problems. The main ideas of these normal forms might loosely be summarized into a set of heuristics or rules of thumb. Note that we think of a list as a table of rows and columns, where each row is a different item in the list and each column records a value that describes some particular attribute or facet of the items that are listed. So here's some rules of thumb. Give each kind of thing its own list and make sure each row in the list is uniquely identified. Add columns to store attributes of interest, and if you need more than one value for one attribute in one row, you will probably need an additional table in your design. Values, and finally, values in one column are not to be determined by values in another column. We'll explain each of these a little more in future slides. Start by listing people, places, and things of interest. For example, a kids club that has badges might need a list of kids and a list of badges. Our first rule of thumb said that each row needed to be uniquely identified. Member numbers and badge names would work out nicely as unique identifiers. Fully normalized data is not allowed to include multi-valued attributes. The second rule of thumb we talked about previously covered this. In the table shown on the slide, listing several badges in one column for the same student violates this principle. Just as we are not allowed to list multiple badges in one column for a kid, as shown above, We are also not allowed to list multiple kids in one column of a list of badges. Why this is bad is not our topic today, but for now, recognize that to list all kids with the hiking badge, you would not be able to just look at the value in the column. You would have to do further processing to break that column into multiple values. The normal solution will be to add a kid badge table. We'll show you that later. Adding a table, as shown here, listing which members have which badges effectively resolves the multi-valued attribute problem. We call this kind of table a junction or intersection table. We might call our new junction table something like badges earned. If a kid earns a new badge, we can add a row. If we realize we incorrectly awarded a badge in our records, we can delete a row. In either case, we do not have to reprocess the data within a column to deal with multiple values. The third rule of thumb dealt with in-row dependencies. Including fields like name and email as shown here is just not a good idea. In case of a changed email address, we would have to update many rows to get things right. Our previous example, where we listed each member in their own row, would be a great place to store information like name and email. Also, note that in this arrangement shown here allows for conflicting data. Check out Sally's email address. Which one is correct? We don't know. In practice, we often denormalize our data structures. For example, big data document stores usually store data in a hierarchical form to boost performance. And sometimes it is easier or more performant to not make an extra table to reduce a dependency. But even if we do denormalize, it is useful to understand normalization rules. It's better to only break the rules on purpose.